Hi there, and welcome to our brand new series Tech Talk, where we invite experts to speak about innovative use cases in virtual test driving. My name is Anna, and today I'm here with Yannick. He is a product manager at IPG Automotive, and he is going to share his expert knowledge with us today.
Hi, thanks a lot for having me.
So Yannick, tell us, what is the topic of today's Tech Talk?
The topic of today's session will be scalable simulation. So basically everything starting from test automation to parallelization up to high performance computing application. I will start off with a quick general introduction to the topic and then take a deep dive into all the technical aspects within the demonstration.
Sounds great. Tell us, why is this topic so relevant nowadays?
Well, 1 or 2 decades ago, lots of discussion focused on trust in simulation for vehicle development in general. And now we move past that point. The need for simulation is without question across the industry now, especially with the persistent development activities surrounding advanced driver assistance systems, as well as later on AD functions, shifted those discussions to how can we simulate more, how can we generate more data in a shorter time frame. And ever since studies referenced requirements of millions and billions of test miles for system validation, highly automated testing processes, parallelization and HPC is now common lingo within the automotive industry.
So the focus is clearly shifting. What are the goals of high-performance computing, parallelization, and test automation?
Well, the main goal might seem quite obvious: to test as many test cases as possible. For example, to identify corner cases for your automated driving function, to tweak the last bits out of your chassis development, or for example, to optimize your trajectory planning algorithm. And so since we are all about efficiency ourselves and experience similar needs on a user level, resource management with regards to time and computational power is a very important topic. So scalable simulation is the answer and the key for all different kinds of simulation engineers and simulation architects.
So there are different user groups. How can they benefit from scalability and high-performance computing?
Yes, so there is a multitude of use cases and user groups, and to illustrate a few challenges, we picked out 3 examples that I want to present now. So the first user is a software engineer working in a startup, picture Silicon Valley. And his main goal is to train his computer vision algorithm with the help of synthetic training data generated by simulation. The second user works for one of the large established companies within our industry. So, for example, OEM or Tier 1. And he's a simulation engineer, a testing engineer, and he wants to go through his testing catalog, resulting in respective KPIs. And the third user group is that I want to take a closer look at is a system architect. He's also working for one of the larger companies, and he is responsible for the tool chain behind, so for the software architecture part.
So what are the challenges these user groups face? Are there any differences between the users?
So the first example is all about financial as well as structural limitations and restrictions. So this user does not have unlimited resources with regards to, for example, a high-performance cluster or cloud infrastructure. So he has to work with what is available within the startup and what he can achieve while programming. The second user does not have this problem. So he does have access to the company resources, for example, cloud infrastructure. His problem or his main challenge is flexibility. So he cannot choose most of the time which tool he wants to use, but he is reliant on the tooling provided by his central IT department, for example. And the last user group is, in my opinion, a quite interesting challenge because he has his user base has different needs and different requirements to his system architecture and to his simulation environment. So he has to merge all of them and also take into account topics like software security as well as efficiency.
Thank you so much for the overview. We are now going to have a closer look at how to solve these issues.
Without further ado, I want to directly jump into the technical demonstration. So, how do you really scale up your simulation? The first thing I talked about was generate synthetic training data for a computer vision algorithm. So I talked about the Silicon Valley startup, and the software engineer there has to generate training data with the help of a simulation tool such as IPG CarMaker. The frame and the challenge are the limited resources. They have to unite employees with different technical backgrounds. But on the bright side, they have very inventive and motivated employees and have a lot of programming experience. The solution and suggestion is the use of containers or containerization with the Docker environment. Once configured, it is manageable for the end users, so it's not hard to run a container. If desired, it can be agnostic to any host operating systems, so it doesn't really matter if some employees use Windows systems and others use Linux systems. And it is very efficient with regards to resources and can be deployed anywhere from wherever. If you're not familiar with Docker technology in general, I highly recommend checking out the tutorials and resources available, for example, on docker.com. With regards to our use case, I want to focus on showing how to run CarMaker inside a container. I'm running a Windows system. I'd rather actually run it on Linux, which is possible as well. But for the sake of this demonstration, I'm using the Docker for Windows application, which is running just fine. First of all, I'm navigating to my build environment, and this build environment contains my Docker file. This is basically copied out of our product installation. So if you're interested, you can actually check it out yourself and try to run your basic Docker setup. The Docker file is the configuration of which you can then create Docker images. In the Docker file, it's just this text file. There is specified which base image you want to use, so which operating system you're running on, which additional software or files need to be included within the image, and which are the mounting points, for example. Off of this Docker file, you then create the Docker image, which I can show right now. And in order to run the multitude of containers for the application you want to run. So while it's building, I am creating a project directory for our software CarMaker, which we'll need in a second. In this case, in the Docker image, there is no standalone installation of CarMaker contained, but we rather mimic the structure of the local system. So we're mounting our project directory as well as our installation directory to the container. First of all, I have to, with the run command, I can now run a container off of the image I just created. By telling him where my project directory is, where my installation directory is. If I finished doing that, I specify the image and the test case I want to run, and of which I want to generate the image data for my use case. Now I can run the container and directly navigate to the sim output folder on my local system. And as you can see, the results are in, and we actually can run as many containers as we want to. We can automate it as well if we desire to do so. So this is a very efficient way of generating data in a very fast manner. Another way of generating the desired image training data for your algorithm is to run the software completely standalone within the container. So instead of mounting directories or volumes, every part of the software as well as data is installed and stored within the container itself. So in this case, I'm running from my Windows host system, but it's also possible, or it's actually easier on a Linux system. For the sake of the demonstration, I want to run a Linux-based container installation from a Windows host. So in order to do that, I have to navigate to my build environment again, in this case Docker standalone. And as you can see in the Docker file, there is now a zip file included, which is the CarMaker installation, and which will be then extracted inside the container and installed there with the batch installer. So first of all, I created the image. I called it CarMaker standalone GUI for general user interface. And now I want to show what I can actually do with it. So completely agnostic from the host operating system, I can run my sensor models in there and then copy the output to my local system wherever you're on right now. So I want to quickly show that. And now the sim output folder should be copied to my local directory, and there it is. And perfect. Another thing that I want to demonstrate is how to actually see the user interface or how to emulate an X server or a display, which will then show you the user interface running CarMaker. This is not a very practical example, but it shows the possibilities you have. So basically, what I'm doing is I'm opening the CarMaker user interface from within the Docker container, and I will quickly show that we're actually running inside the Docker container. Now you can see where the application is running in this 0D and so on. And now I'm showing the process which the Docker container is located. The second use case is to validate development milestones through large-scale testing. Our user is a testing engineer working within a large organization such as OEM or Tier 1. His main goal is to generate key performance indicators from a given testing catalog. In this case, we are looking at a vehicle dynamics application. Oftentimes, you're not in the position to decide which tooling or infrastructure you can use for your tests as a testing engineer. Therefore, flexibility might be limited and the dependency to central IT is in place. Large-scale batch execution in a public or private cloud is the solution we would suggest, and I would like to demonstrate right now. We want to combine this with automated test case generation methods on a local scale, which the engineer can do himself. We are calling two scripts for the automated test case generation. The first one is creating a project and building a custom application with desired models. For example, if I want to include a custom damper model on a C-code level. So now we built our new application and can run the second script, which is creating the actual test case and lots of variations of it. Both scripts are using the APIs of CarMaker, which you can access, for example, via Python. So now, in a second, we can open our own test automation environment, Test Manager, and see that we created 256 variations of the test case via script. What we want to do now is we want to send all those test cases to be calculated in the public cloud, in this case in Microsoft Azure. So I have to quickly log in here. and decide how many cores I actually want to run in the cloud. In this case, I'm using 150 cores, so I can really generate results of 150 simulations in parallel. As soon as I hit start, I can now send all the test cases to the cloud to be calculated there. The test case itself is a simulation of our custom vehicle running approximately 700 seconds. So it's not just a 20-second test case, but rather a long one. And now we can see all the test cases are deployed to the cloud, and all the cores that we started are now running with the simulation. After a little while, we will see that some results are piling in. If we wait a bit longer, then we can see the progress, and slowly but surely the results of the first 150 cores pile in, and the cores directly will grab the next simulation in line and run through all the 256 test cases that we provided and sent to it. As you can see, slowly but surely we're going higher in our success rate and calculate more and more simulations within the public cloud Microsoft Azure. Once we reach our desired 256 simulations, we can think about the post-processing that we want to make. Any results can be processed by tools that our company itself provides within the test manager. For example, generating a report, which I will do in a second, or just get your own scripting off of it and generate diagrams, for example, in Python. After we have the last result in, which is now the case, I will generate a report for an easy overview of all the cases with our tool test manager. And as you can see, all the results are here, and we successfully ran our test with the new suspension model and get the respective results. So this is everything for test case or use case number 2 with the batch execution in a public cloud for our testing engineer in a large company. The third and last use case I want to mention is all about designing access to a central simulation framework. It is about a simulation architect working in a large organization. She is no longer on the application or user level base, but is responsible for the central IT, for the software architecture around the system. The main goal is to establish a robust and secure simulation toolchain. Various requirements and needs of different users have to be incorporated within the system, as well as cybersecurity measures, for example, or other measures for critical system architecture have to be taken into account. Our suggestion or solution for this use case would be a combination of the previous ones. Basically using containerization, but including orchestration or scheduling systems such as Kubernetes and OpenShift, and running it in a cloud environment on or off premise. Where some of the processes and components might sound familiar, the first two use cases are not at all comparable to the third one. The task of the software architect is quite a hard one. He has to manage a multitude of layers of complexity with regards to creating the simulation toolchain and the underlying software architecture. The success of the system architect is highly dependent on company and data structure as well as collaboration of different departments. I want to provide a basic starting point or the basic components in order to start your simulation toolchain or your simulation framework. It is hard to pull off a generic demonstration. We gained our fair share of experience with working with different infrastructures and different tools surrounding it. So please feel free to contact us anytime with your specific inquiry. Basically, there are 3 components you need at least in addition to all the other stuff with regards to software architecture. First of all, the Docker file. Second, there would be the script that you would want to run inside your container to pull off your application. In this case, I'm running a Camera RSI sensor in order to generate my image data in the cloud. And the third one is responsible for the configuration of your scheduling or orchestration tool. With this tool, you can then connect to your public or private cloud and deploy all the containers in order to run there.
Looks like the challenges that you named in the beginning are pretty easy to solve with the right knowledge. Could you once again sum up the different ways users can tackle the challenges they are faced with when working with high-performance computing and scalability?
Yeah, so for the first use case, while financial and structural resources might be limited, one resource is hopefully always available for startup. And this is highly motivated techies eager to find a solution, preferable with programming, and approach with custom scripting regarding test generation as well as executing those test cases in Docker containers is a very good solution for them to work with what they have in their startup environment. The second user working in a large company and trying to go through his testing catalogs in a timely manner, a batch execution approach within one of the larger public cloud providers, such as Microsoft Azure, is a very feasible solution combined with automated post-processing to achieve his goals. And for the last user, the system architect, a very, very interesting topic. And he has to face a lot of challenges. He wants to achieve a holistic benchmark of his simulation environment and simulation framework. So for this use case, we propose a combination of containerization together with scheduling or orchestration tools with an optional usage of private or public clouds. And we think that that's a very good way to do things for him.
In the end, scalability still seems to be a black box for many users out there. What's your advice? Where should users start?
Yeah, so scalable simulation and HPC in particular are very complex topics. Mm-hmm. It involves software, it involves hardware, and most of the times also cooperation and coordination across multiple teams or departments within the company. For a little bit of a technical entry point, we try to present some user examples within this session. But on a broader scale, we gained our fair share of experience working with customers, with users, with partners alike, and basically are happy to help you out.
Well, thank you for sharing your knowledge with us today. It was a fascinating topic. If our viewers have any further questions, can they contact you directly?
Yeah, so first of all, thanks a lot for having me. It was a pleasure. And feel free to send me an email directly regarding the topic, or if you have any general questions regarding the format or any feedback, we're happy to answer all your questions and your emails.
Thank you for tuning in and see you next time.
Thank you. Bye-bye.